It's great to have Jesse Jenkins here. He's an assistant professor at Princeton University, jointly in the Mechanical and Aerospace Engineering Department and the Annlinger Center for Energy and Environment. And he does a lot of super interesting, important, and impactful work on how to decarbonize the power sector and the electric power system, and also generally how to reach net zero emissions economy-wide. Many of you may know that decarbonizing electricity and being able to support new kinds of demands for electricity is a really important part to reaching net zero emissions. And so Jesse has been working on this problem for a long time, and you may have heard about his work. He really does a great job, I think, in sharing this work, with the academic community. He's done a lot of good work to bring energy systems researchers together and help to build that community. And he's also done a great job in reaching out to other stakeholders from government and also from the private sector. So I really appreciate that about his work. We are always very proud to say that Jesse is a graduate of two of our programs. He graduated from the Technology and Policy program here in IDSS, and before it was IDSS, actually, at that time it was the Engineering Systems Division. And then he also did his PhD through the Engineering Systems Division in a program that was the precursor program to our current Social and Engineering Systems program here at IDSS. So, we have been following Jesse's work for a long time, and I just want to say that I was, when we were all sitting reviewing applicants to the master's program, we saw Jesse's application, and we said, oh, wow, this is very interesting. We don't know exactly what direction he's going to go in, but we're pretty sure that he's going to do some important work. So we're happy that we made the right call.
Thank you.
And so I think without taking any further time, I'll just pass over to Jesse. Just two announcements. One is that I think you'll take questions partway at various points through the talk, and then we'll have a question and answer session at the end. And also there is a reception after the talk just down the hall, so you're all welcome to join us for that. Great, well.
Thanks, Jessica. Thank you. I think the last time I was in this room was actually for my defense 6 years ago or so. Jessica was here then as well, so it's a pleasure to be back. It's always great to come back to MIT, and really an honor to be invited to come back to IDSS to give a seminar. So I'm going to talk today, as Jessica mentioned, about the role of clean electricity in decarbonizing the overall economy, and in particular, some of the modeling methods and challenges that I've been working on for the last, 10 or so years to develop tools that can help us understand this transition with more clarity. So 3 sections to this talk. I'll pause after each one for questions, so hold for the end of each of those subsections. I'm going to talk about why clean electricity is so important to decarbonizing the overall economy, and why it's basically the linchpin in our efforts to get to net zero. And I'll talk about why modeling this transition has been so challenging and some of the novel methods that we've needed to apply to be able to model electricity systems in transition, including some of the current challenges that we're facing and some novel methods that have been making significant progress. And then I'll talk about kind of the overall playbook for decarbonizing the electricity sector, which tries to synthesize a bunch of different papers that we've done over the years on different clean generation technologies, energy storage, demand flexibility, and other solutions. All right, so let's start with clean electricity. Why have I spent my last many years studying this particular sector? It's because it plays an outsized role in the overall effort to decarbonize the economy. We've done a bunch of different multi-sector studies recently, starting with the Net Zero America study that I was fortunate enough to join when I started at Princeton in 2019. This was a major effort that came out in 2020 to chart in a high degree of granularity multiple different pathways to decarbonize and reach net zero greenhouse gas emissions across the overall economy. Since then, I've worked on the REPEAT project, which assesses the impacts of federal energy policies as they're being debated and enacted to see how far down the path to net zero we've been able to come. Some of that work ended up in a science policy forum piece that came out on the emissions impacts of the Inflation Reduction Act. And then I've also been able to collaborate with Evolved Energy Research on their annual updates, which provides an up-to-date look on carbon neutral pathways or pathways to net zero for the United States, the annual Decarbonization Perspectives Report. And across all of my work, as well as the rest of the field looking at these problems, we can see some pretty clear overall trends. And it starts, to give clarity, we should start by sizing up the overall economy-wide challenge. And I like to present it this way, which is to look at all of the final energy carriers or fuels that we're going to consume in our economy to provide energy services, everything from lighting to heating to cooling to industrial processes to transportation. And so this is a 2050 frozen policy scenario. It's if we don't care about climate goals, this is sort of where the economics might take us, and it's not all that different from our energy mix today. If we break it down, we can see that about a third of this is already electricity and other carbon-free energy carriers, mostly steam today used in industrial processes, and a little bit of bioenergy, which is at least carbon neutral, and hydrogen. Now, these are energy carriers that as we consume them, emit no carbon dioxide, or in these cases also air pollution. So as long as we can produce these fuels upstream with carbon-free inputs, then we have a kind of full pipeline from production to transportation to use that doesn't emit greenhouse gases. And of course, there are many different ways to produce electricity and steam without greenhouse gas emissions, from nuclear to renewables, supplemented by various things like energy storage. We can use electrolysis to produce hydrogen, et cetera, et cetera. So these are relatively easy to decarbonize. I wouldn't say easy, but relatively easy. The problem, or the bigger challenge, is that the other 2/3 of our final energy consumption are in the form of liquid and gaseous hydrocarbon fuels. So liquids that we use primarily for transportation, and gases that we use for heating and industrial processes. And these solutions, for these sectors, we have much less well-developed or much more expensive solutions that have a much harder time scaling. There are options here, and in the Net Zero America study, we see all of these options applied in varying combinations across the different pathways that we look at. That includes continuing to use fossil fuels in stationary large point sources or in industrial processes that emit CO2 from the chemical processes themselves, like cement production, and capture that carbon at the source and then transport it and store it safely in geologic repositories. We could also drop in carbon neutral substitutes like some biofuels or bio-derived fuels, hydrogen, or so-called electrofuels or e-fuels, where we're taking electricity, carbon neutral sources of CO2, say from the atmosphere or from biogenic sources, more electricity to produce hydrogen, and then even more energy to turn them together into synthetic hydrocarbons. This is obviously a very energy intensive and expensive process. The final option is to continue to just use fossil fuels, particularly in mobile sources, that are hard to capture, and then offset those emissions with negative emissions technologies, whether that's bioenergy with carbon capture or direct carbon dioxide removal from the atmosphere. Now, if you followed any of these solutions, you would know that all of these are quite challenging. They're expensive, right? They're adding significant costs to these pathways. They're very energy intensive, particularly the e-fuels pathways and hydrogen production, as well as negative emissions. All of them are relatively immature, and they have very real scalability challenges. So while they all are going to play an important role, I have yet to see a study that estimates their ability to scale up to meet all of this liquid and gaseous hydrocarbon demand. Right? They simply don't reach that scale, at least at anything that could be plausibly affordable or even physically possible, given limitations on sustainable biomass production for CO2, the ability to scale out CO2 networks or inject CO2 into storage, or to scale up CO2 or carbon dioxide removal to gigatons of scale in just a few decades. What that means is that all of the net zero pathways out there involve some combination of this solution, which is to dramatically expand the role for carbon neutral carriers like electricity and steam and secondarily hydrogen, to shrink the amount of hydrocarbon fuels that we depend on to a level that we can address with reasonable cost and with reasonable confidence that we could scale up the suite of technologies that I just mentioned to tackle the remainder. So we want to grow the electricity share of the pie, shrink the liquid and gaseous hydrocarbon share of the pie, and address the remainder with those more challenging options. Now, this is the final energy consumption in our net zero pathway from the REPEAT project, which reaches net zero economy-wide by 2050. And you can see two things. Not only are electricity and other final energy carriers now 3/4 of the final energy mix, but also the total amount of final energy consumed has significantly dropped, right? That's because when we electrify, we not only switch to a potential carbon-free energy carrier pathway, they're also much more energy efficient thermodynamically. So we get about 3 times as much usable energy from the battery of an electric vehicle to the wheels of the car than we do from an internal combustion engine vehicle. And the same is true for heat pumps, which by just moving energy around instead of combusting it or transforming it, are 2 to 3 times more efficient than even the most efficient gas boilers. So we're getting a final energy efficiency boost at the same time that we're switching on to pathways that are much easier to decarbonize. This is why electricity is so pervasively featured in all of these net zero pathways. Now, what that means is that electricity faces twin challenges, either of which would be hard enough on its own, but together are truly monumental and make electricity the linchpin in our efforts to decarbonize the overall economy. So this is our current electricity generation in the United States. We produce about 4,000 terawatt hours of electricity. Who cares what a terawatt hour is? Just think that we produce 4,000 of them for relative scale. I'll compare it to that later. About 40% of that is clean. Almost all of that, a big chunk of that is existing hydro and nuclear power plants that we're really not expanding. And then the smaller yellow chunk is wind and solar, which has been growing quite rapidly, is now about 12 or 13% of our energy mix and will hopefully continue to expand. The other 60% of our electricity generation, though, is fossil fueled. That's coal and natural gas power plants. And it's the second largest source of CO2 emissions in the US economy after transportation. And it used to be the first. It's just that we've made some progress in recent years in power, more so than transportation, and so they've flip-flopped. So even if we didn't have to expand the role of electricity, we would have to tackle all of the emissions from our current fossil generation by steadily phasing them out and replacing them with carbon-free sources of generation. However, we also have to expand the provision of electricity quite dramatically. And when you combine those, I'll give you a sense of the scale of that challenge. If we were on a net zero pathway, and our policy analysis indicates that we're not quite there yet, there's still a gap, but we're making headway. If we were on a net zero pathway, by 2030, which is now only 6 years away, less than 6 years, we would have to add 1.5 times all current carbon-free generation to the grid in the form of new carbon-free generation. Now, that's almost all going to be wind and solar on that time scale because they're the only technologies that are scalable at that pace in this time scale. Hopefully, beyond 2030, we'll have a wider solution set. But that means that we need wind and solar to go from about 12% of our electricity today to about half by the end of the decade. Then by 2035, the cumulative amount of new clean energy additions from 2022 on would be equal to all of our current generation, over 4,000 terawatt hours. So we have to build the equivalent of today's entire generation mix in under 15 years in all new clean generation. And then we have to do it again between 2035 and 2050 as electricity demand dramatically expands, particularly to produce things like hydrogen, run the remaining direct air capture technologies we might need in the system, and electrify heavy industries, which are the last ones to sort of move in these scenarios. So, it took us something like 150 years from the days of Edison and Tesla to today to build out our current generation mix. We have to add double that over our lifetimes, right, over our professional careers by 2050 to reach these net zero goals. Now, this is, again, as overall energy consumption in the US economy is declining, even as our population and our economy grows, due to the efficiency of electrification. But the electricity sector has a singular challenge of dramatic expansion at the same time. Right? So this is an enormous undertaking. We're going to need to do this in a way that's cost effective, that's well planned, that addresses a whole number of other societal preferences and constraints, and do it rapidly. And doing all those things at once is not easy. Right? So I was recently asked on Earth Day to go talk to my son's preschool and pre-K and kindergarten class about this challenge. And so this is one of those challenges, can you explain what you do to a 5-year-old? And so at the end of it, I summed it up this way, which I think is a nice way to just summarize, not the whole challenge, but 80% of it. Just stop burning stuff, okay? That's actually a pretty profound statement, right? Because like from the dawn of human civilization, when we figured out how to work fire, right? We have built our societies around burning stuff, right? First fire, then biomass more broadly, then fossil fuels, and they propelled us to where we are today. which is that we can now see a pathway to stop burning things in our homes, in our vehicles, and in heavy industry to a large extent, right? Maybe not 100%, but most of it, and to make electricity without burning things predominantly, right? And this is a fundamental shift, right? We can do electrochemical processes, we can run efficient heat pumps, we can use photovoltaics and solar panels, nuclear power to produce electricity in a clean way, right? So this is the bulk of the challenge, right? If you're asked to explain this to your family at Thanksgiving or to a 5-year-old, this is the gist of it. Let's just stop burning stuff. And the more we can displace combustion in our lives with clean sources of electricity, the easier our pathway to net zero will be. Yes, we don't want to burn our vehicles. Yes, we want to. Yeah. All right, so I'll stop there for a minute. I'm going to go on to some of the methods challenges in a moment, but just see if there's any questions there. Yeah.
And the demands on electricity are increasing, and in particular also the conversion of things that were mechanical in the past now becoming electric. Which, why not go back to mechanical processes because they are very efficient and they didn't need that much energy and so forth, right? And so,
in what sectors do you have in mind?
well, little things that in our lives that we now have an electric watch.
Oh, yeah.
And, it's like a little thing, and I don't know how much it adds up, but everything has gone from, simple processes into an electric.
Yeah, simple machines into electric digital machines. Yeah, that's a good question. I'd be curious to think about where in our lives we could switch back in ways that might be more efficient. Yeah, I imagine that, if you think about in your household where the bulk of the energy use is, it's in your vehicle and it's in your space heating and cooling and water heating. And that's, 85% probably of your total final energy consumption. So those are the 3 big ones that I'm thinking of here, but there probably are many others, yeah. And I should say, I'm talking about this electrification demand growth. Like that demand growth forecast was put together before data centers and AI, started to become a headline in the news. I still think those headlines are a little bit overblown because of improvements in efficiency that we see in computing. But there could be other things that demand a whole lot of electricity that are not in our 30-year demand forecast, right? So we should prepare for those uncertain outcomes too. Yeah.
When you're thinking about transitioning the transportation system, are you thinking about one-for-one replacements predominantly of ICEs with EVs, or are you also considering pathways where we move away from car dependency?
Yes. Most of these modeling runs assume pretty much one-for-one replacement. So we have forecasts of vehicle miles traveled and freight miles traveled that don't assume a huge amount of mode shifting. But other studies have looked at broader reconfigurations, and obviously the more degrees of freedom we have, the better our solution set. So hopefully we can redesign our cities in ways that makes using e-bikes and scooters and other things a much safer way to move around our cities and reduce vehicle miles traveled. I got a cargo e-bike to bring my kids to school. In last year, we've already put 500 miles on it. Kids love it. It's way more fun than driving to school in a car. So. But you have to have a safe route to get from point A to point B with your kids. You're not going to put your kids on the back. So yeah, I think there's all kinds of intersections with urban design. The other area that we don't look at is, and we're starting to in our group, is aviation networks, freight networks, rail networks. They're configured the way they are around the capabilities of internal combustion vehicles. You could configure them in different ways if you have a different range of capabilities from, say, electric and hybrid and fuel cell and synthetic LPG and a whole bunch of other different options. And so this is a great area for applied optimization work to sort of think about how those networks could be reconfigured and co-optimized with the uptake and adoption of these new technologies, because they're going to have very different characteristics.
I missed that part. What did you say about CO2 mitigation? How is that working?
So, you mean the targets in this? They're net zero targets. So how do we get all the way to net zero by 2050?
Right, but how about you can capture the CO2?
Yeah, so again, I'm focused on electricity, which is maybe 80% of the problem. The other 20% is we have a bunch of other, so we consistently have CO2 capture in all of these scenarios. You need it for cement, you need it for heavy industry, you need it for biomass capture, because we have a lot of bioenergy in here, and you want to capture the CO2 to either use it or sequester it for negative emissions. So there's a lot of carbon dioxide removal from BECCS, not for power, but for fuels production. And then a little bit of point source fossil fuel use, but very little. Okay. So how do we know this stuff? Like, how do I say with confidence this is what the pathway looks like? How do we model these things? So I'm going to talk a little bit about some of the methods and challenges here, particularly with electricity system planning. Electricity system planning models are decision support tools that have made use of optimization methods for decades and provide a whole bunch of important insight and support for a whole bunch of critical planning processes. That includes utility integrated resource planning in vertically integrated markets where they still do this, where they have regular planning processes that help inform stakeholders in the utility commission about what the utility thinks it should do and why, so they can justify their investments and a rate of return. It's used in competitive markets for investment planning and valuation of generation assets or storage assets or other assets that you might want to acquire or operate or sell. Policy and regulatory impact analysis is also really important. The EPA just finalized their power plant regulations, Section 111D. They did all kinds of regulatory impact analysis using electricity system planning models to try to understand what would happen. We're about to submit a paper that does our own independent analysis of those rules. Indicative planning, that's what the Net Zero America study was. If we want to reach these goals, what would we have to do as a society? No one's actually taking that plan and implementing it because I'm not in charge of the world yet. But it's important, and it helps stakeholders understand the pathways that we can move down, right? And gives them greater confidence to make decisions. And then another specialty of my group is evaluating emerging energy technologies, where the technologies are nascent today. It might be very high temperature thermal energy storage technology, for example, that is going to emerge into the market over the next few years, but won't scale up for another 5 or 10 to have a significant system-wide impact. So we want to be designing those technologies for the possible energy systems of the future, not the energy system of today, and you need future forward-looking planning models to do that. And then you can plug in cool new technologies and see what happens, right? See what happens if they hit their technology goals, which performance improvements are really important to deliver system-wide impact, what do they substitute for, what do they complement for, how does that change the system? So if we go back to before I started my dissertation, and really for 50 years before that, there was a lot of use of these tools to plan one of two types of systems that dominated power systems. In the US, that was mostly thermal systems. So we had a bunch of burning stuff, and then eventually nuclear power, to make steam or gas combustion eventually. And the focus of these models was effectively planning the right balance of different thermal power plants with varying fixed and variable costs. Because power demand is not flat, this is a load duration curve that sorts electricity demand over the course of a year from highest to lowest and typically has this sort of shape to it. You don't want to just have one type of power plant that runs continuously. You want power plants that are suited to the differing utilization or duty cycles that you might have to add up to the overall fleet. So this last little bit of capacity here only operates in this few hours of the year when you have high demand. Whereas this bit of capacity runs pretty much continuously, only ramping down a little bit in this, the trough of demand at the bottom. This is such a simple problem that you can literally solve it by hand. I make my students do this in my class. You just solve the system of linear equations that describe the total cost function for these as a function of fixed and variable cost. So the intercept is the fixed cost of the plant and annualized, and the slope is the variable cost. And you just find the lower volume of these, and you can figure out which technologies are best suited to certain duty factors. The other class are hydrothermal systems, so places like Quebec or Brazil or Norway that have a lot of hydropower. And then what they need to care about is interseasonal and annual variability in rainfall and hydrology. But they still don't really care at all about what's happening on an hour-by-hour basis, because these resources provide huge buffers in the form of large reservoir hydro storage to move energy around in time. And so what mattered was, can I store enough water to get through the dry season or through a drought, not how do I move up or down my hydropower on an hour-by-hour basis. The rise of renewable energy and now other solutions like energy storage fundamentally changes that planning problem. And it requires us to explode the dimensionality of these problems in ways that have posed really interesting challenges for applied optimization. First, the intertemporal patterns of consumption now matter a lot. Right? This is an example of the net demand, so demand minus renewable availability in California over time. We are now at this point where in the spring, the entirety of California's demand can be met by solar power. And so you get this huge trough. And then in the evening when the sun goes down, you have this massive ramp that was much bigger than the old and faster than the old increase in demand that you had to be able to meet with your fleet of power plants. Power plants don't like to ramp up and down that fast, right? And that means that you probably need to have some thermal power plants sitting here at minimum output level, waiting to ramp up quickly, because they also can't turn off very quickly and turn back on again. Ideally, we'd also be consuming some of the power here in energy storage and dumping it into the evening, and the exact pattern of sequences there now matters to the value of batteries or energy storage. So we have to now have a chronologically linked set of decisions that embed operational models of power systems into the planning problem at least hourly resolution, if not better. Second, by relying on renewables, we are now introducing a huge covariance matrix into our problem, which is the covariance over time and space of wind power, solar power, hydrology ideally as well, and electricity demand, which are spatially and temporally correlated by the weather. And so we need to represent this large amount of variation where building a wind farm here is different from building a wind farm there or there, but not totally different. They have some amount of correlation with each other and some amount of correlation with demand. And so now I can't get away with just representing the load duration curve. I need to understand what this covariance looks like and have a very high degree of both spatial and temporal resolution to capture that structure in a reasonably realistic way.
All these renewables are connected to the grid.
Yeah, in this case, we're thinking about grid-connected resources, yeah. And the other trade-off that you get is around transmission. So now you can see this is the best wind resource in the country, and there are indeed some wind farms in here, but there are also some wind farms over here and over here. Why are they there? Well, because we can't just build a transmission line from here to here with no cost, right? And so now we also have to increase the grid resolution in these models to capture, at least at some level, major power flow constraints between areas, and the trade-off between building on a higher quality wind or solar resource with a higher transmission cost or building closer to demand at a lower transmission cost. These are all elements that were neglected in previous models that now have to be simultaneously added into the problem. Plus, this is the average wind availability, but it actually varies quite a lot from year to year, just like hydrology does for hydropower systems. So this is 4 different years of average capacity factor, average productivity of wind sites across the United States, and their deviation from the decadal mean from over this period. And you see the range is plus or minus about 20% variability at any given site. And you can see there's no real consistency around it. This year Texas is bad, this year it's great, this year it's okay, this year it's bad. And so any location can exhibit a significant amount of interseasonal or interannual variability that ideally we'd also be caring about. Because if wind is only 5% of our energy mix, this doesn't matter. But if wind is 30 or 40 or 50% of our energy mix, then a 20% swing up or down has a huge impact on our energy system reliability. So modern capacity expansion planning models should ideally include these features. And I say ideally because it is computationally quite challenging to do all of these things simultaneously. They should co-optimize generation, energy storage, and at least at some level transmission expansion to get the trade-offs between all of those resources embedded in the model. We should have hourly or finer temporal resolution. We should have detailed operating constraints on the intertemporal flexibility of different resources so we can value flexibility appropriately and ensure our system has enough of it. We need high spatial and temporal resolution to deal with the renewables variability, and ideally multiple weather years of potential planning data that we should be relying on. Now the challenge with all of this is that we add more and more detail to these models, it just increases the computational burden. And this leads to, I'll come back to that in a second. The central dimension, the challenge here is that linear programs, which is how most of these are formulated, they scale, the runtime and memory allocation scales quadratically with the size of the problem, meaning the number of variables or constraints in your model. So as you add more spatial resolution, you're adding more variables and constraints. As you add more temporal resolution, you're adding more variables and constraints. As you're adding more locations to build things or transmission lines to expand, you're adding more variables and constraints. And so it's not like doubling the problem makes it take twice as long. It might take 4 times as long, and so on. And so this ends up being intractable at some point, right? Even with the best commercial solvers and access to high-performance computers. So we need to break that scaling law, which I'll come back to in a minute. When I got here and started working on my dissertation, I was probably the 3rd or 4th PhD student to tackle some of these problems, to start to think about how to build power system planning models that were designed to tackle those kinds of new challenges. The previous students had taken their models out the door with them when they left, and so I had to rebuild a new one. My colleague and friend Nestor Sepulveda, who was also here in TPP at the time, was doing the same thing for his thesis. And so we said, wouldn't it be nice if we collaborated on building a flexible tool that ideally we could leave behind and a bunch of other people could use in their theses, so that instead of rebuilding the same model a bunch of times, we can go answer important questions faster. So we decided to build the GenX model, which is now, I'm proud to have met a bunch of people in the audience here that are using it currently still in their research, is an open source model that has been jointly developed and maintained by the MIT Energy Initiative and my group at Princeton. And now, as Darek Malapragada has moved to NYU and my former postdoc Neha Patankar is at Binghamton University, we now have kind of a core team of 4 universities maintaining this model. It's built in Julia and Jump, which is a nice open source programming language for general scientific programming and for mathematical programming. And it's built from the beginning to sort of tackle these kinds of challenges. If you want to check it out, here's the GitHub. What we decided to do at the beginning, the sort of conscious design decision, was to emphasize the reconfiguration of this model so we could have one general purpose kind of Swiss Army knife that could be reconfigured to tackle a bunch of different problems. Because of the computational challenge of these scaling laws, as you add dimensionality along any one of these dimensions, operational detail, time, or the network, or I should also add maybe a fourth one, which is uncertainty, you're expanding the runtime of the model quadratically, or worse in the case of a mixed integer program. And so you're always going to be running up to a limit, either for memory or runtime, for these models. And so we have to judiciously apply the computational bandwidth that we have across the different dimensions in a way that matches the kinds of questions we're trying to answer, right? And because different questions are going to be affected by different structural decisions about your model, you want to be able to reconfigure this tool for a bunch of different applications. As an example, I might be evaluating hypothetical long-duration energy storage technologies in a future decarbonized system. I don't really want to introduce the idiosyncrasies of the New England power systems grid to that kind of question. I want a more generic system that I can test in a bunch of different configurations under a wide range of uncertainties to understand which of those uncertainties really impacts the value of long-duration energy storage. In that case, I might have a single node model. In fact, this is exactly what we did in a 2021 paper, where I'm ignoring the transmission network entirely, and then I'm increasing the temporal resolution to a full hourly resolution for a full year because I'm trying to model long duration storage. And so I want that ability to move power across the year to be accurately represented. And then I'm going to have flexibility constraints from unit commitment on my thermal power plant so I can understand how having storage could make our system more flexible, for example, right? Alternatively, I could be doing a modeling study to look at pathways to 100% carbon-free electricity for a particular place in the world, like the PJM power system or the mid-continent or India, all of which are studies that have been done with GenX. And then I want to represent that system with accurate fidelity because I want to talk to stakeholders in that system and want them to believe that we've accurately captured the key trade-offs there. So now I need to have relatively high network resolution, geospatial resolution. I'm probably going to have to sample representative time periods, but not too few to make the problem unrealistic. I might relax some of these constraints to keep them all linear, et cetera. So really, depending on the question that you're trying to answer, the allocation of your computational bandwidth can be directed into different dimensions. And that's made GenX an incredibly useful tool for a bunch of different research. Which is why we've published dozens of studies using it now at MIT and Princeton and elsewhere. There's about 10 academic groups that we know of, at least, using the model across 3 continents now, an increasing number of nonprofits, utilities, and private sector consultants adopting it also. So very happy that that original vision of like a flexible tool that multiple people could use has not only benefited future TPP and SES students, but an even broader research community as well. Now, this sort of push and pull on dimensionality is what my advisor, Ignacio Perez Arriaga, dubbed the short blanket theorem, which is that we don't have enough computational bandwidth to have a blanket that can cover our entire body and keep us warm all over. So if you want to keep your toes warm, your chest is going to be bare and cold. And if you want to keep your head or your chest warm, your feet are going to be hanging out the bottom. Right? So it's just a silly metaphor to describe the fact that we're constantly trying to expand the size of this blanket, but it's not able to cover all of us and do everything we want of these planning models. That is, unless we can change the scaling dynamics in a very fundamental way so that they no longer scale quadratically with the dimensionality of our problem. So that's something that Nestor worked on in his dissertation here at MIT, and I've continued to pick up and work on in my group over the last 5 years. And we've recently published a couple of papers that make significant progress in this dimension. The central goal here is to take much better advantage of parallel computing capabilities than off-the-shelf linear programming solvers can do. They do not parallelize very well. At most, they take advantage of maybe 8 cores of a machine, which I have more than that on a laptop, let alone access to the supercloud or other sorts of our supercomputing clusters at Princeton, with multiple nodes, with each of which with 50 to 150 cores on them. So we've got all this parallel computing capability, and a problem that doesn't disaggregate and parallelize. How do we chop up this problem in a way that can leverage those capabilities? So that's what we were focused on. And in this paper, we demonstrated the initial problem formulation and a couple of key distinctions over the existing GenX or other similar best-in-class models. The first is that we're now able to model discrete investment and planning-related decisions. That's important for capturing things like economies of unit scale, which are really key in a lot of planning problems. For example, building one very large 765 kilovolt transmission line is a lot cheaper per unit of energy moved over space than building a bunch of smaller 345 kV lines. Right? That's a discontinuous, nonlinear reality that you can't represent in a continuous linear model. As we move into modeling industry, there's all kinds of other examples of where you don't build a small oil refinery, you build a really big one, and it needs to be used at a high utilization rate or you'll shut it down, right? And that kind of binary discrete nature just can't be captured in these other models. So we can now do that. I'll tell you why in a moment. And then importantly, the runtime now scales linearly with the temporal resolution of the model. That means we can add hours or sub-hours to our operational detail. We can expand to cover multiple weather years. We can have more planning stages linked with perfect foresight, all of which now scale linearly rather than quadratically. So we've sort of broken the scaling law in the temporal dimension. That will enable stochastic planning for operational scenarios, which we're working on now. We still linearize commitment decisions to capture the key constraints in the operational model, but it stays linear. And we can represent long-duration energy storage or reservoir hydro systems with accuracy in these models. So how do we do that? Think about a monolithic, large linear program. It has the form of minimize C transpose X subject to AX equals B. The A matrix is the big matrix that is the hard one to invert and therefore drives the computational performance of these models. And it scales based on with rows for every constraint in the model and columns for every variable in your model. And so this is why as you add them, if you add one variable, it now multiplies by all of the constraints and it goes up in scale quadratically. However, if you look at the structure of these matrices, like many other planning problems, they are well structured and sparse. And so we can take advantage of that structure to potentially disaggregate the model. So as an example, a large-scale planning study for the continental US or India or PJM or something where you have a relatively high degree of resolution, with a single weather year, I should say, it gets bigger if you have multiple weather years, and multiple planning stages, say 3 to 5, would be on the order of tens of millions of variables and constraints, so 10 to the 7th. But if we look at this, there's a set of operational decisions for each week or other multi-day period that you can define. It could be 3 days or 4 days or 5 days long, but let's think of them as 7-day, week-long periods, where you have a lot of tight temporal coupling within this because each hour flows into the next, right? And so what happens with energy storage at 2 p.m. links to 3 p.m. and 4 p.m. and 6 p.m. and 9. Same with thermal commitment states for power plants and their ramping, et cetera. But they only link to the next week with this little overlap of the end of the week, right? The few hours at the end of the week tied to the next week. Then we have a set of investment decisions which link all the time periods, because if I build a certain amount of capacity, that capacity will constrain my operations in every time period throughout the model, right? You can't build more than, you can't generate more energy than the power capacity of the power plants you build in all time steps. And then finally, we may have a set of time coupling policy constraints, something like a CO2 emissions cap that sets a budget for emissions across the whole year would constrain the model in all time periods. Because if I pollute more in 1 hour, it reduces my budget in another hour. Reservoir hydro or long duration storage would fit here as well. So first, we reformulate this slightly by cutting the links for short duration operational constraints like battery storage or unit commitment and link the end of the period back to the beginning of the subperiod. This is something that's already commonly done in order to do sample periods out of a larger time series, sample days or weeks, because they're no longer chronologically adjacent when you do that, and you don't want to link the end of sample period 1 to sample period 2, because there might be a big discontinuity when you put those time series back together. So this is a common reformulation in capacity planning models already. But now we have all of these block diagonal chunks in the middle. So then we can use a Bender's decomposition approach, which is a common way to get rid of linking variables, like these investment decisions. And we'll put those in a master problem that now is on the order of a few thousand decisions, the few thousand power plant or factory options or whatever else that you have in your planning model. And now I have a problem structure that is unfortunately still 10 to the 7th or 10 millions of variables, because most of the dimensionality of the problem is coming from all these operational time periods in the model. And they're still linked by long duration storage or policy constraints. What Nestor tried in his dissertation was to embed Danzig-Wolff decomposition, which is another way to typically decompose coupling decisions, or coupling constraints. Unfortunately, that resulted in 2 nested decompositions, which were quite slow to converge. And so instead, we transformed these coupling constraints into coupling decisions. For example, if you have a CO2 constraint that covers the whole year, you simply decide on the budget for each of your operational weeks in the master problem. So now each week, once it gets its budget, is no longer linked to the others in that iteration. And for storage, we simply decide the end state of one period's reservoir has to be consistent with the next period's beginning state. Again, once those are fixed, those become constraints that don't talk to the other periods anymore. Yes? No, we could do that too, but that would be like going from hourly resolution to 2 hourly or 6 hourly or something like that. So this is instead just saying, if I want to carry a certain amount of energy through this time period, I want to accumulate. If I end there, I have to begin there in the next time period. And you fix those budget states in the planning problem. And then we can distribute every one of these weeks, which is now fully parallelizable, across as many cores as we want. So solving 52 weeks takes, in 52 cores, costs the same amount of effort as solving 1 week normally. And each of these is now dramatically smaller. Each week only has about 10 to the 5th decision variables. And now we're actually leveraging that quadratic runtime in the opposite direction, because we've just dropped 2 orders of magnitude in the size of the problem. So these now solve very quickly, right? They solve in a few seconds or minutes. And they all solve in parallel. OK, so now how do we actually figure out what these are consistent with these when they have to talk to each other somehow? So this is the standard Bender's decomposition approach, where effectively we're replacing the operational costs of the model with an estimate of their costs as a function of the planning problem decisions. So I'm basically saying I don't know exactly what it would mean for the operations of the system if I invest in this power plant or that power plant or make this budgeting decision. But I'm going to approximate that function through a series of lower bound approximations or cuts that I'm going to generate each time I iterate this problem. And so maybe this is the actual functional form of that cost function as a function of my planning decisions. And every time I iterate, I'm going to add another estimate locally of how the cost of this subproblem varies as a function of the investment or planning decisions that I just fixed in that iteration. And I'm going to go back and forth, adding additional cuts until I've well approximated the region around the optimal solution, at least. And I can calculate guaranteed upper and lower bounds as I iterate, and stop when it's at an acceptable tightness. Okay, so this is all standard. This is nothing we invented. This is standard Bender's decomposition, decades old, but works very effectively in this context by allowing us to parallelize all of these subproblems once we've made these reformulations. Now, a standard problem with Bender's decomposition is at the beginning, you don't know anything about what the form of that function is. And so Bender's tends to take really wild initial guesses. Like, for example, if you don't know what the operational cost is as a function of power plant investments, and you're trying to minimize cost, the obvious solution is to just don't invest in anything, right? Don't build anything. But then the cost of that is very high. You're shedding lots of demand. You're having rolling blackouts everywhere, and the cost is huge. So what you get back is a very steep cut that's pushing you really far in the other direction. So now you build way too much stuff, and you go back and forth, and it tends to ping pong around for a while. So there's been a set of well-developed techniques called stabilization or regularization techniques that have been applied to Bender's decomposition over the years. We tested 5 of them in this current paper and found that center point stabilization worked quite effectively and gave us like another factor of 5 to 10 speed up over the paper that we published last year. And so this basically helps us move towards the middle of the problem much quicker instead of ping-ponging back and forth. And then the less iterations we have to take, the faster we get to convergence. We also ignore integrality constraints in the planning problem at the beginning until we get our solution to a linear relaxation of that problem, because all of the cuts we get from that are still valid cuts for the discrete problem. And so before we waste a bunch of effort exploring the branch and bound tree for a discrete problem, we should get a well-supported set of cuts that approximate that function, operational cost function, very well, then switch on those integer constraints and proceed to solve the mixed integer problem. So how does all this work? For a planning problem with, again, on the order of tens of millions of variables and constraints, this is a continental US model with 26 zones, 3 planning stages, so every decade from now to 2050. And 52-week resolution operationally in each of those years. The current best-in-class is what's in our current GenX model, which is a dual dynamic decomposition approach that Darek Malapragada implemented that would solve that model in about 30 hours. The problem is its DDP is not parallelizable. It moves forward and backwards, and so you have to solve each stage of the problem in sequence. The performance of our previous paper was not that great. While the scaling laws were good, for small problems, or reasonably small problems, it still was slower than the DDP, although faster than a monolithic problem. Our new solution time is about 5.5 hours for a linear programming problem of this scale as opposed to 30. And then we switch on the integrality constraints and we solve to integrality and close the gap in another 45 minutes or so. So we can now solve a problem with this full scope of resolution that wouldn't just simply be untractable to even put in memory with a monolithic problem, and is taking the current best-in-class model about 30 hours to solve with fully continuous decisions. We can solve now in under 7 hours with discrete planning decisions. So very happy about this performance. Now we've pushed the boundaries back a bit, and we can cram a whole bunch more detail into the model until we break it again, which is what we do. Now, what's motivating a lot of this is that it's increasingly untenable to represent the electricity sector on its own, right? That's what GenX does. We've started to add in little things like hydrogen electrolyzers and flexible demand in vehicles or in buildings, for example. The Mighty team has built out the Dolphin model, which is an extension of GenX that also includes hydrogen, gas, and CO2 networks. But ultimately, what we want to be able to do is model holistic energy and industrial systems in a co-optimized manner. So now we got to add a whole bunch more detail. So the reason for that is this is a current Sankey diagram or energy flow diagram of from primary energy to final consumption sectors of the US economy today, roughly, where you can see the electricity sector, it's slightly, natural gas plays a slight coupling role between buildings, industry, and therefore electricity. And that's been an increasing trend in the US economy. But the electricity sector is still relatively linear. The industrial sector is fairly separate. And of course, fuels are very isolated from one another. And so it's tenable to disaggregate these and model them in separate sectoral models. This is what a 2050 net zero scenario looks like, however, where electricity, again, is expanded dramatically and now plays in every major sector of the economy, where bioenergy is also used throughout, along with CO2 capture and use, which we're not showing here. And hydrogen has become another potential common energy carrier. And so now what happens in one sector is closely coupled to what happens in another, which is important from a planning perspective, that we co-optimize these systems. It's also important from a reliability perspective, because if you have a breakdown in one part of your system, it's going to cascade into others. So I know that's motivating a lot of work in groups here. So we want to now cram a whole bunch more detail into what was already an intractable model. Fortunately, building it on top of this Bender's decomposition and pursuing additional decomposition spatially, we think, on the network component, will allow us to do that quite well. So we're now building from scratch a model built on top of this framework with a better software suite than the Dolphin approach that we were taking, which is just sort of glomming onto our existing model, called Macro. And this is a collaboration, again, with the MIT Energy Initiative, led by Rory McDonald, Darek at NYU Tandon, and my group at MIT, or at Princeton, I mean. And so this is going to be a bottom-up, electricity-centric multi-sector planning model. That's sort of the key differentiating feature from other existing multi-sector models. We're going to retain, ideally, the same kind of resolution that we currently have in GenX, but in a multi-sector economy-wide model. It's built from the beginning for this parallelization and tailored Bender's decomposition. It's going to co-optimize investments across all of these sectors. And ideally, from a software basis and user perspective, it's going to be relatively easy to build out new models of new types of systems with it. So We've got an initial demo that is benchmarked against Dolphin that we're ready to start testing now, and we're going to be building this out progressively over the next few months. As I mentioned, I think we have attacked the temporal dimension of the problem quite well, but there's still a lot of literature out there on network-based decomposition strategies that should be applied in this literature, in this space as well. And so we're pursuing, as our next frontier, a set of network-based decompositions and aggregation strategies that hopefully can keep our subproblems bite-sized even as we expand the sectoral linkages across the model. Okay. All right, any questions there? I'm going to hopefully blitz in a couple minutes through the ingredients of a decarbonized system, but maybe I won't get through all that. Any questions on the methods first? Mm-hmm.
Some high-level information about the network decomposition approaches?
Yeah, I mean, so the basic idea is these networks will only be tightly coupled in certain parts and loosely coupled in others. And so we want to use network partitioning strategies that identify those loose coupling points, split the networks apart, whether that's within an individual energy carrier's network, like the power network or the gas network, or it's the points where they couple across sectors, which is probably the weak linkage points, right? The electricity sector only really couples with the hydrogen sector in the sense that you can produce electricity with, you can produce hydrogen with electrolyzers, and you can produce hydrogen with gas, and you can also produce electricity with gas. So like, there's a couple of linkages there, and we may be able to sever on those. Then there are techniques for aggregation of networks as well. So you can create supernodes that aggregate a bunch of smaller nodes. And our hypothesis is that at the beginning of these iterations, we can solve the supernodes that will speed up our iteration time while still generating valid inexact cuts or lower bounds for our problem, and then expand the resolution as we go. And ideally, we'd like to use machine learning to predict which of those cuts we want, which of those subproblems we want to start unpacking to higher level of resolution first. The ones that are most likely to generate tight cuts are the ones we want to focus on, and the other ones we can remain aggregated. So a strategy like that is what we're going to try to pursue. May work well, it may not. We'll pursue other literature out there. Again, our group does not focus on building fundamental new techniques. What we focus on is breaking down these types of problems so that we can answer more questions that we currently can't answer. And so we're rating the available literature from applied operations research to figure out what works well in this type of problem. Yeah.
But I think if optimization constraint here,
yeah.
Maybe also expanding the tools, right? I mean, now people solve linear programming problems using reinforcement learning.
Yeah, exactly. Yeah.
And they embed solutions into
yep.
networks. I mean, there are parts of this problem where you can learn a module.
Yeah, these subproblems are solved repeatedly with the same A matrix, right? And so I've been talking with Priya here about exactly, and so we think we can use machine learning to either generate cuts themselves or to predict which of them I want to solve exactly and which of them I want to use aggregated.
The size of these problems, even though it's large, isn't crazy in the sense that
no.
reinforcement learning and using techniques like stochastic gradients will actually probably solve these problems a lot faster.
Yeah, it might. Yeah. Yep. Yeah, exactly. Yeah. Well, yes, I think so. We've been trying to do both. We started to do initial just like, can we create an emulator for this problem? It was not proceeding very rapidly. So our current thinking is to try to use ML embedded within the decomposition solution to speed up iterations. And so hopefully some hybrid solution method will work well. But the nice part is now we've broken up this problem, we have our own custom solver, so you can play with these things, whereas once it's in Gurobi, you can't really do anything, right? Yeah. Yep.
I have a question about how your models get used and applied to industry.
Yeah.
Because I guess what I'm understanding is that you guys are running these as sort of like centralized calculation, and in the real world you have ISOs or utilities that are then informing how markets are structured, and there's many stakeholders to that system that are all making their own decisions.
Yep.
Do your models reflect those stakeholder decisions, or are you saying like this is what the optimal power system configuration would be, and let's compare it to the ISO structures to figure out how to impact policy there?
Yeah, so first of all, these tools can be used by all of those stakeholders, and part of our push to make open source tools is to allow more stakeholders access to these kinds of models, and so an increasing number are using them, which is what we would like to see. The way we structure the models, yes, you can represent stakeholder preferences if you want as secondary constraints or objectives, or you can say I'm using this as an indicative plan to say this is what would be the solution if you care about cost, or would be the solution if you care about something else. What we're increasingly doing is trying to explore the near optimal feasible region of these problems. So I want to find all the solutions that are reasonably affordable, however you define that, say 20% more than the lowest cost solution or 5% more than our current cost, because we're kind of okay with our current cost and will satisfy us. That would create a subset of our feasible region for these problems that is all technically feasible. It meets all the engineering and policy constraints in the model and are all reasonably affordable, but may have very different impacts for different stakeholders. And so we're developing techniques to quickly explore that space and then create visualizations and online tools that you could use to explore that space effectively. So that's something Neha and I are collaborating on right now. And we built a prototype model, which I'm excited to, or a prototype dashboard that I'm excited to share with stakeholders. The idea there is you could actually sit down with stakeholders. They could look at the tool and develop an intuition for what trade-offs there are between their own priorities or their priorities and some other stakeholders' priorities, and do that live rather than wait for me to run the model again and then come back and tell them the results. Yeah. Back.
I was curious, I know you mentioned just the tidbit about integration of buildings and transport flexibility, but if you could speak to what that's looking like as well as sort of the simulation of the demand side within the model more broadly.
Yeah, so right now we fix uptake of building and transportation technologies exogenously. And I think we're going to still do that in macro, even though some multi-sector models will embed an optimization of vehicle selection or other things in the model. The reason for that is I don't think that those sectors behave as a system-wide optimizer would do, right? I mean, we have our own limited information and our own discount rates and our own risk aversion. And even if we were perfect quants, we're not seeing the right price signals in most of those cases anyway, because they're intermediated by retail rate design and other things. So the idea is to come up with scenarios, ideally informed by models that other people develop based on either empirics or other logic choice models or other things to inform the design of those building stocks and vehicle stocks. And then we represent their demand profiles in the model. And then we can explore if they're more or less flexible, how that affects the system design. And we've done that in a bunch of studies. So EV charger flexibility or heat pump water heaters or HVAC systems, they trade off basically directly with batteries as virtual batteries effectively. And they dramatically reduce the amount of poorly utilized capacity you have in your system, whether that's networks or batteries or peaker power plants. And so they save huge costs. Like we did a study for New Jersey, 100% carbon-free system for New Jersey, where we had a very modest, I think, amount of flexibility for 2050 in a high electrification scenario consistent with the state's electrification goals, where we assumed, I think, only 50% of EVs were responding to some kind of either retail aggregator or price signal that their computers were optimizing around, and could only delay, meaning they could only charge at night, not at work, which I hope by 2050 you can charge anywhere you want. So this is deliberately conservative, and that heat pump water heaters, about 20% of them were also shiftable forward or backward. No flexibility in HVAC systems, which would be very easy to do as well. So a very conservative solution, and that alone saved $500 million of annual expense in the system, just the bulk power system, because we don't model distribution. It probably saves an equivalent order of magnitude in the distribution network too. So we're talking about like billions of dollars of savings annually just for a state the size of New Jersey, tens of billions nationally. So it's an important piece of the puzzle and something that feeds into lots of rate design conversations and things like that too. Yep.
Suggest if you're comfortable, we can
Yep.
take the discussion.
Yes, and I'm going to leave part 3 off. You can find it online anyway.
Great. Well, let's thank Jesse so much.
Thanks so much.